In the last video for Learning Outcome 3 on probability, we're going to talk about visualizations for probability problems. For qualitative data, we learned bar and column charts, and then we learned pie charts. For quantitative data, we made both histograms and box plots. We know that I said there's three rules to data visualization. That visualization helps you to plan your analysis, it helps you do your analysis, and it helps you present your analysis. That means visualizations are also important for probability questions, and we're going to learn about three different tools you can use to visualize probabilities: contingency tables, probability trees, and Venn diagrams. We've actually worked with contingency tables before. I'm going to just put in the definition that we previously had for a contingency table in lesson 2.1. What the definition was that a contingency table will display counts or percentages of individuals that fall into two or more categories. This can help you to reveal patterns between the variables or about one variable individually and creates what's called a joint distribution. We've already calculated lots of probabilities with contingency tables. We did them for the Titanic data set. However, now that we've actually learned about proper notation for probability, we can now write out our probabilities with a lot more accurate definitions and notation. When you're looking at a contingency table, the individual cells will be the joint distribution. That's the and probabilities that we can represent with the word and or the intersect symbol. When you're looking at the margin totals, so for example, here and here that are in the darker burgundy, those will be the individual marginal probabilities like probability A or probability of B. If you take an individual cell and divide by a margin total, that will be a conditional or given probability. You'll still have to use the rule of complement if you want the not probabilities. And finally, for the addition rule, you'll have to still use the full rule if you want or probabilities, adding any individual probabilities from the table. So the best thing I can do is revisit the data set you're already familiar with, the Titanic data set, instead of introducing a new one. So you can see that now that we actually know the right terms, how can we express these probabilities? So first, what is the probability of dying on the Titanic? So probability dying. For that one, if we're talking about just all the people on the Titanic, we see that there's 1490 that died out of 2,201 in total. That number is about 68% deaths. I'm just going to move it up so it looks a bit more aligned. So that's just an individual probability from the table. What is the probability of being male in the Titanic? For being male, we look at the total males, 1731, and divide again by the total number of people on the Titanic. There's 1731 divided by 2,201, and it's about a 78% chance. What is the probability of dying given you are male? This is where we can start to use our correct terminology. So probability dying given male from a contingency table, that looks like that you take the probability that you're dying and male, where they both happen together, 1364, but you divide by, given you are male, the total males, 1731. 1364 divided by 1731 is about, again, 78%. It is slightly different than this 78% though, so be careful. They are slightly different numbers. What is the probability of being male and dying? Male and dying, you could represent with the intersect symbol or the word and that's simply the people who meet both characteristics. The 1364 people out of all the people in the Titanic because we weren't given a specific trait. It just said dying and male, so it's out of all the people on the Titanic, and that's about a 62% chance. What is the probability of selecting a passenger who died or is male? This one If you want or, it takes a little bit more work. Male or dying. The reason I say it takes a bit more work is that there's not really a faster way to speed this one up. You'd have to do the probability of being male, the 1731, plus the probability of dying, which was 1490, minus where they occur together, the males that died, otherwise you would double count. So this is still using the full addition rule, which says characteristic 1 plus characteristic 2 minus where they both happen together. Using the rules for adding and subtracting fractions, really all you need to do is add the tops and then divide by the number on the bottom, since the number on the bottom is always the same. And that's about 84%. Are male and dying mutually exclusive events? That means can they happen at the same time or not? So are they mutually exclusive? No. There are 1,334 males that died. So yes, they happened at the same time. It's not equal to 0. To be mutually exclusive, there'd have to be 0 people that you couldn't have both happen at the same time. A little bit of a trickier question. Are male and dying independent events? So to get independence, if I go back to the previous sheet, you can check independence by checking any of these conditions. Let's just try the first one. Probability of A given B equals probability of A. In this question, what that would mean is if we take the given probability we found, probability of dying given male, would have to equal the probability of dying for them to be independent. Probability of dying given male is 1364 out of 1731. Probability of dying is 1490 out of 2201. The given probability is about 79%. The dying probability is about 68%. They are not the same number, so that means they are dependent. They have to be the exact same number to prove that they are independent events. This makes sense with everything that we learned about the Titanic data set because we know dying or not has an impact on, or gender has an impact on dying or not because there were more men on the Titanic, more of the men were crew, and less got on the lifeboats as women and children were saved first. So there's the answers to all of these different probability questions using the visualization tool, which is the contingency table. I do have one for you to try. Again, I want you to try this one, and then when you unpause the video, I'll show you the answers. So for this one, I'm just going to write down the answers to speed it up a little bit so you can see how I would get the numbers. So first, for the probability a driver is a cell phone user, I would just take the use a cell phone grand total, 305, and divide by the 755 total people. For the probability a driver had no violation, I'd look for no speeders. That's 685 out of 755. And these, again, are called marginal probabilities. They're taking the value from the margin and dividing it by the grand total. Find the probability a driver had no violations and was a cell phone user. So I'd find where they meet, no violation, and was a cell phone user, it says. So that'd be these people here, use a cell phone. 280 out of the 755, which is about 37%. The next one, find the probability a driver is a cell phone user or had no violation in the last year. For the or probabilities, again, there's not really a faster way to do these besides to do every single piece individually. So probability they are a cell phone user, there's 305 that use a cell phone out of 755. The next piece was had no violation. So no speeding was 785 out of 755. And then you subtract where they happen together, that they used their cell phone and had no violation, which was 280 people out of 755. That will give you about a 94%. Find the probability the driver is a cell phone user given they had a violation. So that would be where they both occur. So speeding and use a cell phone, 25 people. But now, because you're given they had a violation, you only divide by the 70 people that have a speeding violation recorded. That should give you about 36%. And the final one, a driver had no violation given they were not a cell phone user. So look where both happen. No cell phone, no violation. That's 405 people. And because we're given they were not a cell phone user, look at the total number of people that were not cell phone users. That's 450. That gives me 90%. And that's an example of a contingency table to help you visualize probability answers. The next visualization tool we're going to look at is called the probability tree. A probability tree shows choices you can make or outcomes you can get using a tree-like path. They're useful for showing possible scenarios. So in general, how you'd make a tree diagram is you start with a single dot on the left or on the top, depending if you're drawing your tree from left to right or from top down. You then extend roots for possible outcomes, and then from each branch, extend farther branches for the second event that could happen and repeat as necessary. Once you've drawn the tree, you can use it to answer questions like we just did for the contingency tables as well. So I'm going to show you a first tree diagram for the Titanic survival data. So I'm just going to zoom in so it's easier to draw out the tree. So I'm going to draw this tree from left to right. So I'd start with a root that represents the initial choice. And the first event here is supposed to be survival. So that means alive and dead are your only two options for survival. So we have alive and the people that died. We label the tree with the chances that these events happen. So alive, we have 711 people out of the 2,201. And for dead, we have 1,490 out of the 2,201. Those are your first options. And again, the first branch we did was for survival. We're then going to move on to the gender branches. So alive, we'll have two branches out of there for our two genders, female, and then male. And the same thing for dead. You have two options for genders still, female and male. For these branches, for the probabilities, we use the conditional probability. Why we do that is on this branch, for those who are alive, there's 711 people alive in total. So this means you're given that they're alive to be on that branch. So if we look at the females that are alive, it's 344 out of the 711 in total. If we look at the dead, it's 126 females out of the 1,490 in total dead. For males, if I look at the alive males, it's 367 out of the 711 total alive. Just want to erase that circle so you can read it easily. And for males, dead is 1,364 out of the 1,490 in total. Then if you want the total probabilities from the table, so what I mean by that is the chance that you're alive in female, the chance that you're alive in male, the chance that you're dead in female, and the chance that you're dead in male, you'd multiply along the branch. So 711 over 2,201 times 344 over 711. Multiplying fractions, these would cancel, and we'd end up with 344 over 2,201, which is called a joint probability. And we do the same for the males, 711 over 2,201 times 367 over 711. That equals 367 over 2,201. Then we move down to the dead branch. So we did the probability of dying times the probability of being a female given you died. That gives 126 out of 2,201. And then finally, the probability of dying times the probability that you are male given dead. And these individual joint probabilities, these four that we found, 1, 2, 3, 4, they should always add up to a grand total of 1 or 100% to make sure you have not missed anybody or any passengers. And this is just another way to visualize the counts from a table and how it breaks down with each possible option. So you have two options for survival, two options for gender. This shows the probability breakdowns as well as each of the individual probabilities from the table. And that's a visualization using a tree diagram. I do have another example for you. Usually we always do the one together and then try one on your own. The one on your own is about drawing without replacement. So suppose there are 4 red balls and 3 yellow balls in a box. 2 balls are drawn from the box without replacement. What is the probability that 1 ball of each color is selected? So I want you to pause the video here and then try this question. When I unpause it, I'll show you the answer. So in this case, the first choice is related to the first draw. And on the first draw, you have 4 red balls and 3 yellow. So option number 1 is you could get red or you could get yellow. On the first choice, there's 3 yellow balls and 4 red. So for yellow, it'd be a 3 in 7 chance. And for red, it would be 4 in 7. And this is the first pick. That's the first branch. Then for the second branch, we're going to move to the second pick branch. For the second pick, you could get red again in each of the options, or you could get yellow. Those are still our two choices. For the probabilities, if you do not put the ball back without replacement, if your first pick was red, that's for this first branch. The first pick was red. That means there'd only be 3 red balls left to choose from and 6 balls left in the box because we took one out. For yellow, if you chose a red on the first pick, there would still be 3 yellow balls to choose from, but only 6 in the box overall because we've taken one out. If you pick yellow on the first pick, that means that there's still 4 red balls to choose from, but only 6 in the box overall. If you pick yellow on the first draw, then that means there'll only be 2 yellow balls left out of the 3 and 6 balls in all. For the joint distribution, you have to multiply along the line, just like we did here. So you do 4 out of 7 times 3 and 6. This one doesn't cancel quite as nicely, so you could find out what the answer is. 4 over 7 times 3 and 6. It's about 0.29. Let's say. For the next branch, it's the same 4 and 7 times 3 and 6, about 0.29. For the branch down here, it'd be 3 and 7 times 4 and 6. It should be the same number too. Yep, about 0.29. And finally, for the yellow, this is the only one that's different. 3 and 7 times 2 and 6. That's about 14%. Finally, the question asks, what is the probability that one ball of each color is chosen? So if you want red and yellow, that's this possibility on the tree, or yellow-red. It could be red-yellow or yellow-red. So probability one each color should be about 0.29 plus 0.29, or about 0.58 approximately, not including the more decimals. Again, we did not include red red because that'd be the same color, or yellow yellow because that would also be the same color. We only want the probability that you get a ball of each color, which is those middle two options on the tree, that you get red and yellow or yellow and red. And the tree diagram helps to show this relationship. So you can easily just add those two probabilities and get your final answer. So I hope you were able to map that out and see how to visualize it, and that seeing the solution now also makes sense. The last tool we're going to look at is the Venn diagram. They're named after the person who invented them. So Venn is the last name of the mathematician that invented the Venn diagram. And Venn diagrams are a very helpful way to visualize probabilities. So in a Venn diagram, you represent the sample space with a rectangle, and every outcome will appear inside the rectangle. Then, if you have any event in common, that would fall in the middle or overlap of the circle. So for example, this is circle A and circle B. If you say A or B both could happen, that's inside both circles. A and B, them happening them together, is where they intersect, the middle. This would be not A, everything outside of A in the Venn diagram context. So again, this would be one circle represents A, one circle represents B. Where they overlap is where they have the and probability. That means where they occur together. And outside of the circle is everything that is not that event. That's the complement. So let's do a Venn diagram representation together for an example that we looked at previously, that A is the event an odd number is rolled, B is the event the number 1, 2, or 3 is rolled, and C is the event that an even number is rolled. So back to our examples that we've looked at previously using dice, because those are some of the ones that we're most familiar with. So if A is odd, that'd be 1, 3, or 5. B is 1, 2, or 3. And C is even, 2, 4, 6. So if I wanted to do a Venn diagram of this situation, I would want 3 circles. 1, 2, 3. And they're all inside this big sample space, S. I'm going to zoom in on it a lot. So let's say this circle is A, this one is B, and this one is C. A has 1, 3, and 5. The 1 is shared with B, the 3 is shared with B. The 5 is by itself. It shares nothing with C. So 1 and 3 have to go in both A and B, 1 and 3. 5 is only in A. So this is where A and B only meet. This is where A and C meet. This is where all 3 meet. For B, we already got the 1 and 3 that it shares with A. It also has a 2 that it shares with C. This is where B and C meet, but not A. The 2 goes there. If it was here in the middle, that's where all 3 meet. And finally, C has just the number 4 and 6 to itself that are even. That's only in C and not in the other ones. So having this Venn diagram can help you with probabilities, because if you say something like, what's the probability that you're in B and C? There's only one number, 2, that's in both. Or what about being in A and B? There's 1 and 3 that are both A and B. What about A and C? There's nothing that's in both A and C. That's empty. What about A, B, and C? That would have to be this piece in the very center. There's nothing in there, so that's the empty set. A, B, and C share no common elements. So this helps you with some quick probability calculations so you can visualize what events are shared or where the overlap is. I want you to try a question using a Venn diagram that's very, very similar to the one that we looked at for the library card. This one, number 4, that I said was tricky, it's actually easier to solve using a Venn diagram than trying to use like the rule of complement kind of idea, like I showed you previously with complements for B and not B. It's a lot easier to just solve this one using a Venn diagram. So I want you to try to use a Venn diagram for this question and then use it to answer these 5 questions. So please pause the video here, and then when you come back, I'll show you the full solution to all the parts of the question. So my first step is I'm going to try to draw the big Venn diagram over here, and then I'll use it to calculate all the probabilities individually beside the questions. So here's my full sample space, S, and we have 2 events in this question. We're told 40% belong to a club, 50% work part-time. So this is club, this is part-time. 5% work part-time and belong to the club. I'm just going to move this one circle over a little bit to make it easier to see what they share. More overlap. So club, part-time. So if there's 5% that do both, club and part-time, in the middle, 50% work part-time. So this whole circle for part-time needs to add up to 50%. If 5 is shared, then that'd be 45% left over for people who work part-time but don't work or belong to a club. And for the percent that belong to a club, it was 40% in total. So if there's already 5% in the middle that do both, it'd be 35% left over. So if we have the picture that looks like this, 50%, 45 plus 5 is 50, plus 30 would be 80, plus 5 more is 85. Then we have 15% left over that do neither. In the sample space, that's the complement. For the complement of everything outside of the circles, all in here, everything outside the circles, that's the 15%. If you have a Venn diagram that shows all of those elements, then it's very easy to answer all of these questions. So what is the probability that a student belongs to a club? That's given in the question as 40%. You don't even need the Venn diagram for that one. It's just in the question. If you want to write it out with full probability notation, which we should probably do, I'll write that out first. Probability club, 40%. What is the probability a student works part-time? 50%, given in the question. What is the probability a student belongs to a club and works part-time? Again, that's given in the question. Club and part-time is 5%. What is the probability a student belongs to a club given that the student works part-time? This one you will have to use your formula for. Probability club given part-time. First you take that they both happen together, and then you divide by the one after the given symbol, part-time. So club and part-time is 5%. Probability part-time is 50% from our previous 2 answers. 5 divided by 50% will be 10% chance, 0.1 for the answer for that one. And finally, the last question, probability club or part-time. Club or part-time. For that one, according to our addition rules, you'd have to do probability of club plus probability of part-time minus probability that they both occur. We already know that should be 85% based on all the percents that are in the circle. That it should be probability of club is 40, probability of part-time is 50, minus the probability they happen together, 5%, and that gives 85%. Everything that's in the circles for the Venn diagram. I just want to go back before we conclude the lesson to this final example that I said would be a little bit easier using the Venn diagram. If I just expand this last piece so I can make a Venn diagram for it, I'll show you how it's a bit easier using our Venn diagram way to solve it. So if this is DVD and this is book, we're told in the question that the probability of getting a DVD is 40% and the probability, the probability of a book is 40% and the probability of a DVD is 30%. In the second question, we calculated the probability of both as 20. So that means together would be 20. If book altogether was 40%, that'd mean 20% is left over in just the book. And if getting a DVD was 30%, that'd mean 10% is left over for just a DVD. So when we ask for probability DVD but not getting a book, what that's asking for is everything that's in the DVD circle, but it can't overlap with book. So it does not include that and overlap. With the Venn diagram, you can easily see that's 10%. It's in the DVD circle, but it's not overlapping with book. Only 10% chance of getting a DVD and not getting a book, which is the same that we did using the equation earlier, but it's much simpler to visualize in the Venn diagram structure. So that's the last example that I wanted to show you. There's many, many more examples in the free online textbook. I have chosen a number of specific questions that are similar to the questions that we did in the lesson today, and those are in Moodle under the Learning Outcomes section. If you go to the Moodle page and then scroll down to Learning Outcome 3, you'll see the homework questions from both of the lessons there. This time, because probability takes a lot of practice, I did assign questions that have most of them have solutions from both the practice sections of the textbook and the homework section. So you might see some more questions than previously, but for probability questions, a lot of them are short and about the same situations. The links will bring you directly to those sections of the textbook here. If there's any questions you cannot get the answer to, after you've seen what the final answer is in the book, please send me an email or come see me in class if you're a student that's in the in-class section, and I'll be happy to assist you. Thanks so much for watching this video. That will conclude Learning Outcome 3 on probability. As always, if you have any questions, don't hesitate to reach out.